It's 10 past, so I think I'll get started. Friday, we made it. So thank you for coming. This is a session, I'm going to be talking about 96 boards and specifically about building hardware. So this is a fun session where I get to talk about things that I actually don't know a whole lot about. But it's, I've been doing a bit of hardware design over the last 6 months, specifically for 96 boards to get things up and running. And learned an awful lot in the process. I'm going to be talking about what I've learned, but I'm not really the expert. And there's actually, if there's questions, there's probably going to be questions that I don't quite have the answer to, but there's people with far more experience, such as Andy Green over here, and Akira in this room who have more experience with hardware than I do. So, but we'll get started. So I thought I'd start with the quote from Alan Kay. Linaro is a software company, yet why are we doing hardware? I get asked that well, fairly frequently. I like Alan's quote. People who are really serious about software should make their own hardware. And that comes down to a bit about why we're doing 96 boards. So by and large, 96 boards is a software project. We are doing 96 boards very much because it enables our software goals. It allows us to solve the software problems that we want to by having hardware that's under our control. This really got highlighted in our latest release, the 1603 release. The whole team, everyone who was involved, did an incredible job. We've now got a single Debian set of Debian images. That same kernel image boots on over 6 different platforms out of the box, both device tree and ACPI, both enterprise and consumer, both 96 boards hardware and our members' enterprise hardware. It's been incredible, but having the boards to work on has really kind of focused our development and highlighted the things that were missing. There were, when I was working with the sensors kit, it was, as I was going through the releases and bringing things up on Dragonboard and HighKey, I was finding the gaps, and I was finding the places where the two boards differed. And it really brought into relief where work needed to be done. So once we got to the release, we can write applications that work with the expansion connector, completely binary compatible. The application will be portable between both Dragonboard and HighKey without any changes, without recompiling. And so now we've got a really good software base, including support for I/O expansion. So this is hardware supporting our software activities. But 96 boards is not just, it is not merely enable our software activities, they're also real things. Qualcomm has had incredible success so far already with the Dragonboard. The HighKey board, same thing. It's a fantastic board. These are devices that others are taking and they're able to make real products with it or use it for prototyping their own designs. So we want to have these, we want to see the support available and the tools available for engineers to build what they need to build. How do I build a mezzanine? Have an idea, do something, and then profit, right? So, I'm talking about hardware design. I think the big message that I want to have is that hardware is, we want hardware to be, we want you to think about hardware as a possibility, that we don't always go to, I've got a board, I need to solve a problem, but I don't have the hardware, so I'm going to work around it. No, I want you to be thinking of hardware as one of the options in your toolbox when you hit a software problem. However, disclaimer, I'm not saying everyone should design hardware. What I'm saying is that when you hit a software problem that hardware could possibly solve, let's talk about it. But I'm not claiming any responsibility for burnt fingers or slipped schedules or breaking your boards. This is information to know what is possible. Why build a mezzanine? Or why even consider building a hardware, and why are we having this session? To begin with, hardware design has never been easier. When I started doing electrical engineering, all of the design tools were very proprietary and certainly beyond my reach. I did not have $1,000 or $10,000 for a reasonable schematic capture package or PCB layout package. 10 years ago, we had, I think, a package called GEDA, which it was great open source package. It was an absolute bear to try to use. I mean, you obviously have some experience with it. So we now are at a place, though, where we have tools that we can actually do this. So when you're thinking about if you need to build a test jig, or if you have an idea of how you could use the board in a different way, we currently have all the tools that we need to do this at our fingertips on our Linux installs right from day one. So what I'm going to do for the rest of this session is I want to talk about two things. The first thing I want to talk about is, as software engineers, so this is a session for software engineers, how to get comfortable or how to know what is possible with hardware design. Either if you want to try it out yourself, or have enough knowledge to know what it is that you're asking for when talking to a hardware engineer that you're working with. So I'm going to start with that. And then the second thing that I want to talk about is 96 boards specifically, on what are the design considerations and what are the constraints that you need to be thinking about if you're building a mezzanine design for 96 boards. I've got an electrical engineering degree, but when I did my electrical engineering degree, I liked the software. I was always writing code, and I wasn't paying nearly enough attention to my electrical engineering classes. So I did know the theory, which helped, but when it came to trying to build a board for the first time, when I did the UART adapter, I found it was very intimidating on, well, what do I do next? How do I choose, what is possible? How do I get the PCB done? How do I even use a soldering iron? All of those things there was a lot of barriers on what to do. So, fortunately, we have the internet. There's certainly lots of resources out there. I have nothing but good things to say about the starter kits that are already out there. Arduino has got to be the easiest place to start. You can get an Arduino starter kit that will get you through the basics of electronics very quickly. And just going through, if you want to be comfortable with the electronics, going through a bunch of sample projects is a really easy way to get started. So go and get the starter kits. Solderless breadboard is your friend. You're going to want to that's a good thing to start with as your tools, to have a toolbox of basic components, a breadboard, and to wire up to an Arduino and prototype things. Having good skills, getting comfortable with using a breadboard also ends up being your primary prototyping platform as you're thinking about how you're going to do a hardware design. And it really becomes a whole lot easier when you've got a project that you personally are interested in. So I got into my head a few years ago that I want to build a lightsaber. But I want to build a lightsaber that's a little bit better than the toys you buy in Toys R Us. I found these WS2812 LED strips, where each LED on this long strip is individually addressable. So if I use one of these LED strips, I can build a lightsaber where the light grows up from the hilt and then comes back down. And so I did this, I've got a little picture of it there, and I did this project with my kids where I took some evaluation boards, bodged them together, hooked them up with the LED strip, and put a few controls onto the handle, learned how to mount it, went out to the hardware store and bought pipe to build the handle. And this was something that kept me going in the project, where I had a goal as opposed to just mucking around with the electronics. So if you've got a thought of something that you can build, it helps to get going. Once you're comfortable with the basics, then start taking a look at the tools. As I said, we've got just about everything we need. I've got a couple of them up here. My personal favorite for doing actual design is KiCad. KiCad's been around for quite a few years now. And in the last year or so, it's started to become really mature. This is approaching basically professional grade schematic capture now. You can do multi-layer boards, you can do the schematic and the PCB, you can do 3D modeling. It has advanced routing tools such as differential pair routing, and also it will do push-pull. So when you're drawing your traces, it will push and move traces out of the way as you're doing things, or as you're trying to get everything to fit. Really quite slick. Another one that I haven't used much, but a lot of people like, is fritzing. And if you go and look at fritzing, you install it. It starts off with a picture of a breadboard, and you're able to drag and drop modules and wire them together. But what's really interesting about fritzing is from the breadboard prototype display that you can reproduce on your desk, you then can switch over to the schematic tab, and it's got a schematic of the design that you've just done. And then you can also switch over to a third pane, which gives you the PCB design. And they've also wired it into some services of where you can go to actually get PCBs printed. So it's worth a look. I don't personally use it, but a lot of people like it. Many people use Eagle. Eagle is an option, is a free option for many developers, but it is proprietary, and it is limited to 2-layer boards. So if you're comfortable with Eagle, a lot of board shops already have designs produced by Eagle, and they're a little bit happy, or they're more comfortable with that. Just be aware of the limitations there. In both the case of KiCad and Eagle, though, all of the design files are text-based format, which is comfortable for us and software engineers. There's also design tools available when it comes to actually building the hardware. I'm not even going to talk about 3D printers. But there's, aside from OpenSCADA, which is solid modeling, also very accessible to us software engineers, because rather than being based on typical graphic CAD design, it is based on programmatic. You basically write code that describes what 3D object you're wanting to create. Laser cutting, Inkscape is a great tool now, and is cross-platform Windows, Linux, Windows, and OS X. LibreOffice, if you're going to build something, you need documentation. You can have really nicely printed graphic user guides. And then, of course, our standard workflow. One of the things that I think us as software engineers can be bringing to hardware design is we have very well-established processes for revision control and how to work with text files. All of these tools now, all the open source tools, tend towards the text-based file formats, which means there's been times I've needed to make a change, and I could have gone into figured out how to do it within the tool. But if I need to make a change across the whole directory, I can use sed. I can use my existing tools to do search and replace on the text file. So, you got the tools, you spend the time, you start making a design. How do you actually get what you're designing onto your desk, preferably without spending a whole lot of money or spending a whole lot of time? This is where the maker community has really helped us out here. In the last few years, again, it's become a lot easier to get PCBs printed, and it's become a lot easier to get PCBs assembled. Used to be that makers there's all kinds of techniques that you can use for printing PCBs at home. Pretty much all of them are messy, and pretty much all of them require a bit of time or effort to figure out how to do it, and you're probably going to go through several boards before you get one that works correctly. Now, if you want a PCB, there's 3 right there that are cheap, that you can probably get 10 boards printed for around $10. Dirty PCBs, OSH Park, Seed Fusion PCB. I've used OSH Park and Seed both. They're good quality boards. Generally with PCBs, it depends on how fast you want to get the board back. If you want to get the board back fast, you spend a little bit more money. But if you don't mind waiting a couple of weeks, OSH Park and Seed Studio, it's almost pocket change to get the boards. Then you need to assemble it. More and more of the technology is moving towards surface mount components. But all of this stuff you can still do at home. To begin with, if you do a design that's through-hole parts, that's always the easiest because you can put the components in one at a time, get your soldering iron, flip the board over, and solder all the devices down. But it is actually, with so many parts available on surface mount, it is feasible to do all of that surface mount stuff at home. There's guides online. I won't try to get into that in this session, but there are guides online on how to do surface mount either by hand soldering or, as a lot are using, when you print the PCB, get a template printed as well so that you can put solder paste over the board, place your components all in the places, and then put it onto an electric frying pan and reflow the solder that way. Toaster oven. Toaster oven works too. Again, internet's your friend because lots of people are doing this, and lots of people have done this and screwed up doing it, and then posted videos online about how they screwed up so you can learn from them. You don't have to do it yourself though. If you've got a design, you just need to get it onto your desk. There's also plenty of assembly houses. Again, I've used Seed to do prototype assembly. They're reasonably fast. And it's not an awful lot of money. It's more than pocket change. But if you've got some work that you need to get done, prototype assembly service is probably within your budget. You don't have to spend a lot on this. And they will also handle not just assembly, but they'll handle the sourcing of the parts on your question back here.
When you say within your budget, you mean within the budget that your company's going to fund?
Okay, so I, of course, use broad generalities here. You can get, well, I'll use the example of Seed. They have a service called PCBA, and you can, if you use parts that are all within their catalog of kind of pre-approved parts, and they list that, you can get an online quote of how much it's going to cost, and it can cost, $100. I mean, it depends on the size of the board. So for the run, yeah, yeah. I did that with the UART board, which is a very small board. It didn't cost me very much to do a couple of boards prototype, but I won't say anything more than that because there's so many factors that go into the cost of a prototype board. What I will say is just go to the site. Seed's not the only one who do some searches, find the places that will do online quotes, put your BOM in there and see what it will cost you. But we're not talking about thousands of dollars anymore. We're talking much lower amount of money. I mean, there's been some projects where it's low enough that even for my hobby projects, I would consider it. If you get to the point of a design that you actually want to get more than onesies or twosies on your desk, there's resources available for us to actually get into manufacturing as well. You probably don't want to do manufacturing yourself unless you've got the time or you've got the people to put onto it. Start with, if you do prototype service for PCBs or for assembly, start with talking to whoever did your prototype runs because they'll already be familiar with your design. But again, lots of companies that are more than willing to do a production run for you. Also, when you start talking about real production runs, these companies are a great resource not just to produce your design, but also to give you feedback. So a good manufacturing house should give you design for manufacturing review. They should give you feedback on what you've done and what you could change to make it easier to manufacture, easier to test. And they should provide testing. So if you're going to be shipping something in any kind of quantity, you'll want to have, some level of testing to go along with it. Sales and marketing, I'm just an engineer. I won't even talk about that. Okay, 96 boards. So I'm assuming you're in here. We've got, lots of us have 96 boards on our desk. We want to build something that builds on the 96 boards base. So I'll go through some of the design constraints that you should be thinking about if you want to build a board. So I'm going to assume you're using KiCad. Tried to get some tools out there. There's a template that an intern student at Linaro has put together that will get you up and running on KiCad very quickly. There's the URL. These slides will be available online. You can also find it on the 96 boards GitHub page. Clone that, put it into your templates directory in KiCad, and use that as your start of your product. There's nothing worse than going and doing a hardware design, printing the board, mounting all the connectors, and finding you've put the connector off by a millimeter or two. Having the template, make sure you've got that stuff sorted out ahead of time. Or fork an existing design. We've already got open source designs out there that you can make use of. I mentioned the UART board. I also did the sensors mezzanine. The UART board is just a small board that just is the size of the low-speed connection. So for very simple designs, you can use that. Sensors mezzanine is the full size. It has already on the design the USB UART. It's got level shifters. It's got a power regulator and a bunch of connectors plus an 80 mega microcontroller. You can fork that design. You can rip off all the things that you don't need and then add whatever circuitry you're actually interested in. There is already the sensors mezzanine. I know of another board that's being produced that started with that design. And then Michael Welling has done a really good job, really good board that's up on GitHub right now, which he calls the RoboMezzi. And that one has a bunch of hardware on it for doing PWM and other inputs that would be needed for robotics projects. There are a couple of the RoboMezzi boards here at Connect this week. Tyler Baker has them. And Cohen, I think you're getting one of them. Cohen back there plans to build a robot with one. The sensors, oh.
Sorry, what's his license system?
I believe I put BSD license on the UART and the sensors mezzanine. BSD. I need to double check if that's the best license to use, but my goal is to be a permissive, completely open license. Always check the license if you're cloning an existing product. Always give credit if you take an existing product. I mean, if you use Michael's board, I didn't tell him I was putting his board up on this slide. If you use someone's board, just, give credit where credit is due and follow the license. But I mean, we're doing open source hardware here for a reason. I want people to be able to use these designs as a base. Mechanical, that picture did not turn out at all. If you look at the template project, there's nice dimension drawings on it. But you can go to the 96 board spec. It shows you all the constraints that you should have. You can make there's a couple of options that you have when you build something. With the mezzanine board, you've got the low-speed 40-pin connector. You can either build a single board with pins on the bottom, or you can build a stackable board. If you build a stackable board, some things to watch out for is watch out for the maximum height restrictions that are for the baseboard spec, because if you build a stackable board, you have to conform to those height restrictions as well. You can either use just the low-speed connector or a combination of low-speed and high-speed. If you use low-speed only, plan to mount with standoffs. The low-speed connector on its own doesn't have a lot of strength mechanically. If you use the high-speed connector as well, you've got a little bit more. It's a little bit more solid. And I also recommend preferring surface mount components, simply for the fact that with 96 boards, we're trying to keep the height quite short. So there's a 7mm separation. If you put through-hole components in the wrong place, and we discovered this the hard way with the first sensors board, if you put through-hole components in the wrong place, the pins short against the USB connectors on the baseboard. Don't do that. If you do surface mount, especially if you're going to go into manufacturing, surface mount is going to be cheaper to manufacture because they can put everything down and they can run it through the oven. And you also have a better density on what you can get onto the board. I had no idea what I was doing when I was starting using surface mount. I had no idea even what footprints were. First thing to do, find someone, if you can, who has already done a few hardware designs to give you a little bit of guidance, because you're going to have a ton of questions on what footprint am I supposed to use? How am I supposed to do that? I would say, generally starting with 0603, this is a specification or a description of a specific footprint for 2-pin components like resistors, capacitors, diodes. These are very, very common. That's a good place to start for all of your passive components. Every component that you use will have a data sheet. Go find it. Those data sheets should have detailed footprint information at the bottom of that. When you're doing KiCad, when I started, I thought, this is easy. I'll just do the schematic. I'll do the layout. Someone will have done the footprints for me. No. Plan on when you're working on this, you're going to be, for some of the components that you're putting on your board, you're going to need to be making your own footprints. That's just normal in electrical design. There isn't a good database yet of open source, of footprints for common components. There's a few databases out there, but it's going to be hard to find what you need, and more often than not, it's easiest just to take the data sheet, put in the dimensions that you need, and then add that to your design. I also found it extremely helpful to look at other open hardware designs and see what other people were doing and just steal that, or just copy what they were doing for choice of components and how they solved the problems that I was seeing. Looking at other designs is a great source of inspiration and a great way to learn how common problems get solved. Power supply. There's 3 sources of power for the mezzanine board. You've got the DC in, which is 8 to 18 volts. Be careful, don't short it accidentally to any other pin, because that's the end of your baseboard. You can supply power from the mezzanine board, or you can supply the mezzanine from the baseboard power. There's also the regulator power pins. There's a 1 amp 5 volt pin, and there's also a 1.8 volt 0.1 amp. If you have any kind of power requirements on your mezzanine board, you're going to want to regulate down from you're most likely going to want to regulate down from the 5 volt rail. The 1.8 volt, I would recommend use that mainly as the IO reference voltage. The spec for 96 boards currently says 1.8 volts is pin 35. I've been proposing a future revision of this spec has a key pin cut out so that we always get the board oriented in the right way, and redefine the 1.8 volt as IO voltage. Now, the reason I mention those two things at the same time, because if we do make this change, it's not going to be compatible with all mezzanine boards. So the key pin would be part of that. Of the new designs would be, if you've got the key pin in there, then the VIO line might be higher than 1.8 volts. I've got, for example, the UART design is 1.8 volt only. But the sensors board design would happily use pin 35 as VIO. I'm going to get to IO voltage in a moment, but when we've got different SoCs that we want to use on 96 boards, some of them are low voltage mobile chips that are 1.8 volt IO. Some of them are more industrial focused chips that have 3.3 volt IO. Trying to have a spec that handles both of those turns out to be rather hard. volt I/O. There's been more than a little discussion about our choice to put 1.8 volts I/O on the connector. Turns out transparent level shifting is just plain tricky. If you want to, for the first 96 boards, we were using mobile chips, 1.8 volt. We could have specified putting transparent level shifters on the base board. If we did, first of all, it does take a lot of room to put level shifters on. But also, I've found it's really easy to confuse the level shifters that I've used. Some of the level shifters, if you want to do high-speed level shifting, there's not a whole lot of I/O drive. And if you put too much capacitance, if the traces are too long or there's too much load on that line, some of these level shifter chips get really confused and go into oscillation. And it's difficult to figure out what exactly is going on. Putting the level shifters up on the mezzanine means that you can choose the level shifting for what you need to do. You've got several choices. The easiest level shifters are one-way buffers, where you use transistors or resistor dividers, which works when there's only one direction of I/O. If you need bidirectional I/O, there's the two common styles. The most common is clamp style, which is on both sides of the level shifter, you draw the voltage up to the I/O voltage of that side of the signal. And then, when one of them drives the voltage down to ground, it activates a transistor and brings them both to ground. That's what a BSS-138 MOSFET or a PCA9306, those essentially do the same thing. The PCA9306 is designed for I2C, and it happens to have two MOSFETs in one package. So it's a little bit more compact. The problem with the clamp style is that you've always got those pull-up resistors. So when you're driving low, you're drawing a little bit more current. And it also means that when you stop driving low, you have a bit of ramp time as the voltage level comes back up. Not a problem for I2C, is generally not a problem for 100 kilohertz. But if you get into high-speed signals, the clamp style doesn't work very well. There are some solutions that work faster. TI has two chipsets, TXS 010, 24 or 8, 246 or 8, and then TXB 010, and then again 24608. The last number is the number of channels that are on the chip. These are high-speed level shifters, and they have accelerator circuits in them that when it notices the signal coming high, it triggers a one-shot that drives the signal high so that you can have higher speed transitions. They get really confused though when they've got too much load. So when I was trying to use them, I put them down on the first and second revision of the sensors board. And I had two problems. First of all, for the 1.8 voltage, I had a few I2C devices that couldn't get the I/O voltage low enough. And I also had, when I plugged with the Grove cable, plugged it in, I would start to get oscillation on the line. And they're great for onboards, they're great for high speed, but if you're trying to do anything with on expansion connectors, it's probably not going to work. I had to, on the Rev C of the sensors board, I had to rip these off and replace them with BSS-138 MOSFETs. The other thing I'll mention, I had mentioned clamp style. There's also the push-pull style of the TXB is nice because it doesn't have the pull-up resistors. You don't have current draw when you're driving it low. But the amount of supply current that you can get out of there's a little state machine in each channel of the TXB device. And it kind of monitors, and when it sees one side change transition, it drives the other side up there, and then it goes back into a steady state of just kind of holding those signals there weakly, which allows either side to drive it to the other direction. Works for level shifting, but it changes what kind of devices you can hook up. If you're doing SPI, the TXB works great. But if you're doing I2C, which depends on that draw, that pull-up behavior, the TXB doesn't work at all. Some specific things, I2C, test on a breadboard before you commit to a board. I2C was my biggest source of headaches. Probably a lot of that was due to my own inexperience, and folks like Andy would have a lot more experience with that, but not everything plays well together. So don't just assume from your data sheet that things are going to work together. Prototype, try things out. If you are doing a prototype board, I mean, that's fine. Just be aware that your I2C, you're going to want to spend some attention on. Typical I2C requires pull-ups, as I said. 1K is, I see that in a lot of designs, but again, you have to be aware of your devices. I have, for example, the Grove RGB LCD module. It doesn't have very strong drive strength when it's driving low. So if there's 1K pull-ups, you can't see the Grove LCD. And I had to put 10K on the sensor board to work with the widest range of devices. UART. There's 2 UARTs on the expansion board. UART 0 is available for applications. UART 1, by default, is the Linux console. We've got it on the expansion board. You can, if you're doing a management type board, you may want to consume the outputs, the I/O from UART 1. If you're not using UART 1, I strongly recommend passing that through to a header so that you can actually hook up a USB cable. On all of my board designs, I put the FTDI chip on there because that's the use case. SPI is defined on there. I have to admit, I have not played with SPI yet, so I can't say much more than that. It defines a chip select line, but SPI is pretty, I mean, any GPIO line can be a chip select. So if you want multiple SPI chips, just use some of the GPIO lines. There's 12 GPIOs. There's not much more to say about that. Power button and reset button are pulled up to the top. Word of warning, right now, because of the PMIX that we're using, the actual behavior of the power and reset buttons will change between boards. If you hold down power, it's still power up or power down the board, but the behavior is slightly different just because it matches the use cases that were on the mobile devices that they were designed for. We are, for the next, hoping to resolve that in the next revision of the spec. These are some of the things that you discover when you start a new project, and it's just the little things that you didn't expect would be, didn't even think about because you were concerned about other parts of the spec. But anyway, it is there. It's designed to be hooked up to a momentary button, or you can use, if you want to manipulate it from a mezzanine board, you can drive them. Driving low will activate. I2S, again, I've not done anything with that, but the pins are defined. You should be able to put an I2S codec on the top board. And that leaves 10 minutes for questions. So, we'll go here first, and then Cohen.
Yeah, the UARTs there, you mentioned UART 1 is the default for the console. Is that specified anywhere?
It is not in the spec, and it needs to be.
Okay, because the UART 1 is optional on the low-speed expansion, so if you have an SoC that doesn't implement that UART 1, it kind of violates that idea.
Yeah, so there was a big fight about UARTs when we first released 96 boards. After things have been released and after we saw all the boards that are out there, we made the decision after the fact that we need to have some more conformity between the boards, and that's why we've since made the decision. Look, we're going to push everyone to use UART 1 as the default, and we're going to. So the next version of the spec needs to specify that. Okay. So, Cohen next.
So, ESD protection.
ESD protection. You can probably answer that. I will say so quickly, no, you can probably answer that, because
I'll answer it easily. Yes, it's a good idea, and we don't have as much as we'd like.
yes.
It actually ties together with it. Like, go for it, Andy.
Yeah, so all of the silicon that you see in these devices is the I/O is specified for something called 2 kilovolt human body model, ESD. That's just to allow it to survive in the world. And for touching it or most kind of consumer use cases, this is enough. But for I/O that will go out, stuff like USB connectors, things like this, they need extra protection and use a spec which is 8 kilovolt human body model. So it depends on the I/O, but the I/O on the SoC will all be okay for at least a 2 kilovolt spec, so it won't just blow up. But if you're taking long wires or you expect to connect to other equipment, then you should use diode protection. There's a type called transorb diodes, which are rated for very high surge currents and used to protect stuff along with the 2 kilovolts already on the SoC. So you can buy this and add it quite cheaply.
Just a couple of plugs. If you're going to build hardware and you think you've got it finished, either grab an IR camera or grab an infrared thermometer and check your board in most of the states, because if you're driving something that you've built and you weren't paying perhaps as close attention to the spec sheet as you should have, you may be driving stuff right at the edge of heat, and you pretty much want to know that before producing a large volume of them. I've seen that mistake made many times. And another thing, I'll throw out a plug for maker spaces around the world. If you don't know what you're doing and you want to learn, check and see if you got a local maker space, because in many cases they're doing surface mount. They've got all the equipment you might need to be able to properly do it, microscopes, proper soldering stations with anti-static and everything that you might want. So just as a kind of look around, if you want to learn, there's probably somebody that's out there that really wants to help you do it. And a last pitch, if you're going to build a mezzanine board and it needs software underneath it to drive it, please use one of the 96 board approved libraries and drive it so that it'll work on from any 96 board, not just the one you happen to have. So libsoc or the Intel library, grab it, it's there intentionally so that it'll run with any of the 96 boards.
Yep. In fact, with the Debian image, it's not packaged right now, but those libmria, libsoc, libupm, those are all going to be packaged in the near future. So you just install them and it will work. Okay, other questions? All right, well, thank you very much.